So, number 5, quarterback can throw a receiver a high lazy lob pass or a quick fold pass. These passes are indicated by curves 1 and 2, respectively. Alright. So let's see, they start and stop at the same height, and they have the same range, which I know just from my general knowledge means that their angles must be, what is that, I think it's complementary, add up to 90 degrees. Remember we have that symmetry around 45? So whatever angle, launch angles I have are going to be that. So I might even actually put that into my y here. It'll be a general y, so number 5. Oops, I'm going to have to pause for a second. Alright, so now that we have a pen that's a little more reasonable size, I'm going to note that the launch angles would add to 90 degrees. The launch pad starts with initial speed, and its time of flight is this. What is its launch angle? The bull pass throw with launch angle 28 degrees. What is the initial speed of the pass? Oh, wait a minute. If they have different speeds, then they don't have the same complementary angles. Okay. Alright, so this we want to get rid of, since they're not at the same speed. So we might start off with that the ball is a projectile. Thus, only influenced by gravity. Still feel like I'm writing really big. All right. So I might actually also add in here by thinking that the y dimension controls the time more than the x dimension. Because I think that's the y dimension is going to be more restrictive time-wise, because it's changing. The x is just going out for as much time as we have. So, in my how, let's start with part A, which tells me the lob pass. It tells me the initial speed, but doesn't tell me the direction. That's why they want the angle, and the amount of time that's in the air. And from my graph, I know that it starts at 0, and in the x direction moves out to 35, and in the y direction it starts at 0 and ends up at 0. All right? So, and then I can grab, let's grab some from my equation sheet. I'm going to be here in my accelerations equations. I think the main one I'm going to use is that main position equation in the middle, although I may use some other equations here to make life easier. All right? But since I know the time, we're probably going to do a bunch with time equations. All right, let's see what we can tackle. So, give myself a little diagram here to start off with. That my initial velocity, 21.4. At some angle, I'm going to call that theta. So vertically, it's going at 21.4 meters per second sine theta, and horizontally, it's going at 21.4 meters per second cosine theta. So right away, to make the math easier, I'm going to break it into x and y. What's it doing in the x and what's it doing in the y? Because those are independent of each other. And so in the y direction, I know it's starting here, it's going up, stopping, coming back down to here. All right? And whatever velocity it started up with here, call that v naught y, it's going to end up with that opposite velocity. That's what this is, v naught to the y direction. Right? Because it's landing at the same height. It has just the same amount of time to go up as it has to come down. Now that's not true if it doesn't land at the same height. But since it does, I'm going to use that factor. And so from my equation sheet, I'm going to pull that v final equals v initial plus a delta t. And I'm going to use, my v final is going to be negative because it's downwards. 21.4 meters per second sine of theta. My v initial is going to be upwards, 21.4 meters per second sine of theta, plus my acceleration is negative 9.81 meters per second squared, because I know that it's a projectile, so the only thing influencing it is gravity, and my time, I'm told, is 3.97 seconds. And I can do a little calculating and find out what theta is. Yeah?
Why is it, why did you come up with 4 negative this time?
Oh, because I assumed, because this class always picks that up would be positive and down would be negative. And when I throw something up, it goes up, and then when it comes down, it's moving down. Right? Because if I didn't remember that fact, what would happen with my velocities? They'd cancel out, right? So I'm actually left with a little simplification. Sine of theta equals 9.81 meters per second squared times 3.97 seconds over 2 times 21.4 meters per second. And I get theta in. Now, one thing you want to be careful on your calculator is make sure you are in degrees. And sometimes you'd be in radians from doing math. And make sure you have your order of operations correct. And I get 65.5 degrees. Let's let's see, did they want, and they want 360, so that should be right. All right, onward and upward. Oops, I should box that answer, right? And on to part B. So, part B. The bullet passes through a launch angle of 28 degrees. What is the initial speed of this pass? All right. Do we expect the initial speed to be more or less than the 21.4? Oh, you guys have thrown footballs. Which do you throw it harder, when you throw a big loping pass or a line drive? Line drive. So, all these, it will mimic reality. So, all right. So now we don't know the amount of time, right? We know the horizontal distance, which is called the range. We know the vertical motion, but we don't know the time. All right? And we know what launch angle it's at. So this one's actually slightly trickier in that we need to use both horizontal and vertical together. So, we'll start off, we'll draw our initial V0, and we're going to break it into its components. So here is 28 degrees. So in the X, we know that's V0 cosine 28 degrees. And in the Y, it's V0 sine 28 degrees. And I'm going to have to actually do sine and cosine. Neither one alone is going to give me enough information. I know that just from experience. I'm going to use the equation, let's see. Well, we'll probably use V equals D0 plus V initial delta T plus 1/2 A delta T squared. And since it lands at the same height, I think I'll also just prime myself. I'll probably, sorry, that was supposed to be an F. Too bad. Probably use this one again also. Just thinking ahead. So let's see how far I can get in the X direction. In the X direction, I know where it ends up. I'm going to use this one in the X direction. So I know it ends up at 35 meters. It starts at 0 meters. Its initial velocity was V0 cosine 28 degrees. I don't know the amount of time. 1/2. I know, what's the acceleration in the X direction of a projectile? Well, what's unique? What is the condition for something to be a projectile? Influenced only by gravity. What direction does gravity act in? Downward. So how much of gravity points horizontally? None. So how much of its acceleration would be horizontal? 0. All right. So I really can't go any further. I mean, that goes away, right? And that whole term goes away. But I don't know V0 and I don't know delta T. So I'm kind of stuck. Don't have enough information in the X direction. In the Y direction, this is where I'm going to employ this equation. I know, same condition as we did in part A, it's going up. and coming back down to the same height, so I know that it moves at the same speed, just the opposite velocities. So I can use that fact again. I can use negative V naught cosine 28 is its V final. Its V initial is V naught cosine 28 plus negative 9.81 meters per second squared acceleration, and I don't know, again, delta t. Darn, I can't go any further there either. Oh, but wait a minute. I have two equations and the same two unknowns. Oh, I think math tells me that's solvable, right? I think it does. Double check your math teacher, but I think it does. So I could put it into Wolfram. I could substitute in. How? What do you guys think? Which way should we solve it? Substitution or Wolfram? Sorry, I missed. Okay. So the one person that was loud enough to hear said Wolfram. Okay, so let's try it with Wolfram. The only thing you've got to kind of be careful of with Wolfram is it assumes that your angles are going to be in a radian. So I'm going to actually figure out what my cosine of 28 is. Oh, wait a minute. Those aren't cosines. Oh, I'm glad I started to do that. I knew it was Tuesday morning. Those aren't cosines. Those are sines. You know, I'm feeling algebraic this morning. Let's just do it with algebra. Because I can solve this one for delta t, right? And I just get 2 V naught sine 28 degrees over 9.81 meters per second squared. And if I solve this one for delta t, I get 35 over V naught cosine 28 degrees equals delta t. 35 meters, sorry. Excuse me. So I have 35 meters V naught cosine 28 degrees equals 2 V naught sine of 28 degrees over 9.81 meters per second squared. And then I can just solve that for V naught. Maybe we'll do one more math step. Right? There's my calculator. Here it is. I suppose I should have a 2 down there. my answer. Oh, that's why I don't like my answer. The 9.81 should be up here. Darn, algebra in the morning. So, we'll put the 2 there. There we go. That looks more reasonable. Yeah, that's much better. I get 20.4 meters per second. Alright, part C is pretty much, they want to know the time of flight for the bullet pass. So what you can just do is substitute in either of your expressions for delta t and figure it out. I'm going to use the x one just because it's easier. So I'm just going to, I had that 35 meters over v naught cosine 28 degrees equals delta t. And I'm just going to substitute in I could have done it on either one that I was comfortable with, though. That was the advantage to solving them both for that. Yeah, a lot of people will probably make mistakes in order of operations, so just be careful of that. And I got 1.95 seconds. Which makes sense, it would be a faster pass. Alright, so we're going to do 13. You've got a baseball player slides into third base with this initial speed. What is the coefficient of kinetic friction? Kinetic because he's moving relative to the ground. And the ground is this. What is the player's acceleration? They kind of leave out one little thing that you have to assume. What is the one fact that we're assuming? Well, really two facts. That the ground is flat. We're not like sliding downhill upper. Excellent. There's one other thing you probably assumed so quickly that you didn't even have to think about it. Okay, yeah. Actually, yeah, that would matter. Yeah. That wasn't the one I was thinking, but you're right. That once you hit the base, you stop. All right, that's the other assumption. All right, so this one involves forces, so this should be a force diagram, I think would be the best Y for this one. So in our force diagram here, this is number 13, ground, baseball player. Let's say, what base are they going into? Third. So we'll put the base over here. That means their velocity is in this direction. All right? They would have a force of gravity down on them, a normal force perpendicular to the surface, a frictional force opposite their motion, and an acceleration opposite their motion, because I know they're going from some high speed down to zero. So their acceleration must be opposite their motion. And yay, that'd be my whole diagram. So on my equation sheet, I'm going to look in accelerations. But what I'm going to really look at is under forces again, because I have my Newton's second law and also my frictional force equation. And I'd probably look back up because I'd remember what my gravitational force or my weight equation was. Then we can go here, go down below our how. I'm going to use this, and this, and this. So, some of the forces in the y equals MAY, just like we were doing for those multiple days, and some of the forces in the x equals MAX. So I'm going to break it into components right away, because looking at my diagram, I've got a couple forces in the y and a couple forces in the x direction. Which way do you guys want to call positive? Which way in the y direction? Up? Okay. And which way in the x direction? To the right? All right. So in the y direction, I would have positive force normal plus a negative F sub g will equal m times 0, because there's no acceleration. So force normal equals F sub g, which I know equals mg. In the x direction, I only have one force, and it's in the positive direction. That would be my frictional force, and m, and then my a is in the positive direction also. So this is mu force normal equals ma. Oh, I know force normal. So mu mg equals ma. M's go away. I'm left with mu g equals a. I know mu. It's the coefficient of friction, and they tell me, and that's 0.48. So 0.48, and it's unitless, times 9.81 meters per second squared equals A. And then I can find A.